Welcome to the LemnaTec Academy. In this video, I will explain the analysis of multispectral image data created using LemnaTec's multispectral systems. Let's start with a comparison of different imaging techniques. First, we have RGB imaging. With RGB images, we record just 3 color channels in the visible spectrum, mimicking the human vision. Each of these channels is quite broad, covering some 100 nanometers of bandwidth. On the other side, we have hyperspectral imaging. With hyperspectral imaging, we have much more individual channels or bands, and each of them has a narrow bandwidth of about 1 nanometer. The spectral range is also wider, covering the visible range and the infrared range, up to 2500 nanometers. Multispectral imaging is somewhat in between. We have more channels. These are defined by different colored light sources. These have a bandwidth of some 10 nanometers, but with longer tails. And these colors may overlap. In addition, we can use filters to narrow down the result further. RGB images are taken quickly within a few seconds. A hyperspectral scan can take much longer. But all channels are recorded in one go. With multispectral imaging, each image is taken as quickly as an RGB image. But we need one separate image for each channel or band. In order to record RGB images correctly, we need to adjust their white balance. This is usually done by LemnaTec, but you can readjust it to your needs. Before hyperspectral scans, a special white target is recorded. We measure here the maximum value we can expect from each channel and at each position of the scan line, so we can correct for it in the analysis. We must do something similar in the case of multispectral imaging. Here we adjust the exposure time for each color channel such a way that the record intensity of the light reflected from a white target is the same for all channels and all filter settings. This is usually done by LemnaTec. You will find matching sensor unit configurations on your system. These imaging technologies differ in their measurement and analysis capabilities as well. With RGB images, we can do the traditional image analysis to measure morphological features of plants and plant parts, including some types of color analysis. With hyperspectral imaging, we can use various vegetation indices which combine the reflectance at different wavelengths to reveal something about the inner workings of the plant. We can further compare the spectra for changes associated with certain conditions of the plant to get some spectral signatures. In principle, we could do the same morphological and color analysis as with RGB images, but at a much lower resolution and with a lot more effort to reconstruct an RGB image from the spectra. The multispectral approach provides us with many options we have in the RGB and hyperspectral imaging. We can create RGB images using 3 images taken with red, green, and blue light. We can even vary the blue and red light sources to get a quasi-RGB image, which might be easier to segment. We can then execute the same analyses on these images as for images taken with a real RGB camera. You can select this mode in the sensor unit configuration in Lambda Control. This will directly create this RGB image. On the other hand, we can calculate some vegetation indices like NDVI, in particular if we apply the relevant filters. We can also analyze spectral signatures in a coarse-grained fashion, in particular around the red edge. And we can measure some fluorescence responses by activating some molecular system in the plant using the light at one wavelength, like UV or blue, and measure at another wavelength using a filter. This way we may measure the chlorophyll fluorescence. Let's have a look into some examples of multispectral image analysis in more detail. The first example I like to address is the NDVI. In order to calculate the NDVI with multispectral data, we need two images. One using NER light and the other using some of the red lights, red or deep red. You may improve the quality using a filter around 680 nanometer. If you're using this filter, the far red light might be used as well. We can now use these two images and combine them into one signal using the gray calculator device from LemnaGrid. I will demonstrate this later in this video. You may calculate other indices in a similar way. For each of the required wavelengths of the index, you shall pick one of the light sources close to the required wavelengths. Optionally, narrow it down further using a filter. Then use the gray calculator device of LemnaGrid to calculate the index. For the wavelength maxima of each light source in your multispectral imaging system, please check your manual or ask us. Your system can be equipped with up to 5 filters. Please choose them carefully for your intended use case. The second example I like to address is the chlorophyll fluorescence. You may activate the chlorophyll using the blue light. Then you can take an image using a filter in the red spectrum at 680 nanometers or so. Due to the bell-shaped like emission spectra of the blue light source, we still have a little intensity at 680 nanometers. But the peak of the blue light is far away enough to be fainter at 680 nanometer than the chlorophyll fluorescence signal. However, if you want to measure other fluorescence signals like GFP, make sure that the activation light is dim enough at the fluorescence wavelengths to actually see the fluorescence signal. The final example is more qualitatively. We have usually 4 or 5 light sources around the red edge. NER, far red, deep red, red, and maybe yellow. You can use these to assess the curve at the red edge qualitatively. You may even be able to derive an indicator for some condition from it. For instance, the red edge might be shifted towards NER under certain conditions. In this case, the signal in the far red channel is reduced and you may use this as an indicator. But now let me explain how to extract these values in LemnaGrid to perform an actual analysis. The analysis of multispectral data in LemnaGrid is quite simple. It uses basically techniques I've shown before in other videos, like the color analysis video in class 3. In this video, I will focus on the NDVI analysis. First, we need 2 or maybe 3 readers, one for the red and one for the near-infrared channel. The third reader is a channel which we use for segmentation. Possible options are the RGB image taken by the multispectral camera, the far red channel, or the near-infrared channel. You need to check the images of your experiments to find out which works best for you. In this video, I will use the RGB image for segmentation. I will add the color threshold device and use the value mean mode. Since this plant contains reddish leaves, I use only the brightness, the white channel for segmentation, with a value of 34. Then I add the usual morphology. Then I add two fill holes devices. One for the foreground with a threshold of 200 pixels, and one for the background with a maximum hole size of 100 pixels. Finally, we need to convert this into objects. Up to here, the procedure is quite familiar. Now we need to calculate the NDVI. But first, we need to convert the red and near-infrared images into actual grayscale images. Although these images are actually already grayscale, the disk universal reader outputs them as RGB images, which happen to contain only gray colors. We use the RGB to gray converter to do this. Here we select just the red channel. Now we feed the output of these two devices into a gray calculator. Input A of the gray calculator is the red channel, and input B is the near-infrared. The NDVI is the intensity at 800 nanometers minus intensity at 680 nanometers divided by the sum of the two. Therefore, we need to calculate B minus A divided by B plus A. The NDVI formula does not define how broad these bands should be, so we can use the red and the NER channels as a replacement. If we want to be more precise, we may add filters at 680 and 800 nanometers during the recording. However, this was not done in this recording. Red near infrared minus red divided by the sum. The result is pitch black, and it seems to be I have only one value. As I told in other videos, this is normal. This does not mean that we have miscalculated anything. It is just that LemnaGrid expects values between 0 and 255 for the visualization, and the result for the NDVI is between 0 and 1. We may fix this by multiplying with 255. The results looks now much better. However, if we want to work with the NDVI and average it later in this process, it is better to keep the values between 0 and 1. As you can see in the tooltip, we have still some variation in the values, which are now between 0 and 1. Now we have a segmentation and a grayscale signal representing our NDVI. In order to combine them, we use the mean color property device as in the color analysis. In order to combine them, we use the mean color property device as in the color analysis video. Finally, we will send this result to an objects writer. We may use the NDVI image as an input to the objects writer. However, However, we need first to amplify it and convert it back into an RGB image. Although this RGB image will still contain only grays. Now we can configure our writer. As we can see in the tooltip, we have an average NDVI for this plant of 0.3. I think the value is so low here because our plant contains a lot of grayish leaves. We may do a few variations to this grid. We could use the deep red instead of the normal red. This gives an average NDVI of 0.38. If we use the far red, we get almost no NDVI value. The NDVI value is now at 0.05. This is because the far red is already too deep inside the red edge. That said, if you have a filter at 680 nanometers available in your system, far red with this filter may work as well. Maybe even better than deep red, because the far red LEDs are much brighter to begin with. Another variation is using false color images for the representation of the NDVI. For example, using the palette gray to color device. Or we may use the RGB image instead of the NDVI image. If we want to measure some fluorescence signal, like the chlorophyll fluorescence, it's even simpler. We may use the same channel for segmentation, in this case RGB. We need just one of the other readers and input to the one main reader the image which was recorded using the correct filter. We can omit the gray calculator and the amplifications. If we connect the output of the reader now to the mean color property device, we have our grid. We can apply the same variations as before. Since we don't have a dataset available with such a setting, I cannot demonstrate this any further here. One crucial part is to give the readers meaningful names. This is important with any grid, but even more in this case. We not only must make sure that the image from the correct cameras is sent to the reader, but also using the correct settings, aka the correct light. In LemnaExperiment, in the Analyst Definitions editor, we must make sure that this combination is correct. Deep red goes into the red reader. NER goes into the NER reader. and we take the RGB image from the RGB camera. Please note that the multispectral camera can act in two modes. The multispectral mode, which creates grayscale images taken with a specific light source and filter, and in pseudo-RGB mode, creating an RGB image from 3 grayscale images. In Lambda control, these two modes are represented by 2 cameras, although there's actually just one camera in your system. The camera side RGB here is the multispectral camera in pseudo-RGB mode. In the output translations, we get the average NDVI value from the average color parameter. For instance, from the mean color green. This analysis definition is now automatically saved, and you can use it to analyze your data. In this video, I gave you an impression on analyzing multispectral data. The analysis in LemnaGrid is fairly straightforward. The key is the selection of the light sources and filters for the individual images, and the combination of these images, as I have shown you in the first part of this video. See you in another training video.